ऑन कर दिया. ओके. So the coupling efficiency is very important component of fiber optics, and as the efficiency in other cases, efficiency को generally हम eta से ही define करते हैं. This eta is equal to mainly क्या है, output work है ना. This is output work upon input work. ठीक है. तो कोई काम कर रहे हैं तो आपका आउटपुट कितना मिल रहा है और उसके पर अचीव करने के लिए इनपुट में कितना आप एफर्ट कर रहे हैं, तो इन दोनों के रेशियो को हम इफिशियंसी कह देते हैं. यहां पर भी जैसे कोई फाइबर है, अभी हम इसको डिटेल करेंगे. फाइबर है तो कितना इनपुट में ये दिया गया पावर और आउटपुट में कितना पावर मिल रहा है, तो इसकी रेशियो आउटपुट अपॉन इनपुट को हम फाइबर कह देते हैं इफिशियंसी. अब कपलिंग इफिशियंसी का मतलब हो गया कि ये सोर्स यदि है और सोर्स को कपल करना है, जोड़ना है एक से दूसरे, तो कपल करने के लिए जो टेक्निक यूज किया जाता है उसकी क्या इफिशियंसी हो. सो दीज थिंग्स दैट वी हैव टू डिस्कस टुडे. तो हाउ टू डिफाइन इफिशियंसी, कैसे डिफाइन करेंगे, तो इट इज मेजर ऑफ amount of optical power emitted from the source that can be coupled with optical power in case of optical fiber, है ना. Mathematically it is expressed as eta of coupling C is equal to P of C upon P of S. P of C means power covered with optical fiber upon PS is power emitted from optical source. It is also known as launching oblique coupling efficiency. And depends on the types of fibers attached to source and also the techniques of coupling. techniques of coupling. The light emitted from source and exposed to the core within acceptance angle, theta A. Within acceptance angle theta A is coupled and the light incident at angle greater than theta A, that is acceptance angle. So if we take this case, then we can classify two categories. Suppose this is a source, this is source, and here it is fiber. Here it is the fiber. So radius RS or RA, radius of fiber. Radius of fiber, something like this, RA. And this is the radius of source. Radius of source. Now, the acceptance angle is something like this. How much it is incident? So, for the measurement, we can draw this diagram, a bigger diagram, something like this. This is the part of conical ray from source, and this is fiber. This is fiber. So this part is cladding. This part is the cladding, and here it is core. Inside is core. This is RA, is the radius of core. Now the angle, this axis is there, and from this axis, if this is R is the angle, and here it is the angle theta. This is the theta. So this R radius is resolved in two components. This is R sine theta, and here it is R cos theta. This is R sine theta and R cos theta. This particular angle is d theta. So this part is which is the appear as the ring shape, that is ring of R into d theta. thickness of this ring is r into d theta. It is the r and here it is theta, so it is r into d theta is the part. And the first thing, and the second is, suppose this is the I0 and the deviation is theta over here. So this is I0 cos theta A. I0 cos theta A is I. Intensity at this particular angle. So using these two concepts, consider the elementary area of core angle theta dA area. So area is length into breadth. Length into breadth. तो लेंथ किसका, मान लीजिए ये एक कोई, दिस इज योर लेंथ L, this is L and here it is B. So this is L. This is L into B. What is L? If the r sin theta is the radius, so this is r sin theta radius into 2 pi. 2 pi r sin theta A is the perimeter. And what is B? B is the width. Width is r into d theta. So this L is 2 pi r sin theta A into width is r into d theta. R into d theta. So what is this? Is 2 pi r square, 2 pi r square sin theta into d theta is dA. Sin theta d theta is dA. And power fed is intensity of source into area. Intensity of source into area. That is I cos theta into area. So this is I 0 cos theta A into 2 pi r square sin theta into d theta. Sin theta into d theta is this is the power fed. So from this expression, we have consider the source of radius RS is smaller than the radius of fiber core RA. That is RS is less than RA. And having cylindrical symmetry, but very close to optical fiber, very close to optical fiber. The coupling efficiency, is expressed as eta C is equal to 0 to theta A I 2 pi r square sin theta d theta upon 0 to pi by 2 I 2 pi r square sin theta d theta. So this part is cancelled. This is 0 to A theta A, I is equal to I0 cos theta A into sin theta A d theta upon 0 to pi by 2 I0 cos theta A into sin theta A d theta. So we can express this 0 to theta A, 0 to theta A, I0 by 2 into sin 2 theta A d theta upon 0 to pi by 2 I0 by 2 sin 2 theta d theta. So we have this cos theta 2 theta 1 by 2 of 0 to theta A upon 1 by 2 cos 2 theta 0 to pi by 2. So this is cos 2 theta A minus 1 upon minus 1 minus 1. That is 1 minus cos 2 theta by 2. So this is 2 into sin square theta by 2A. So sin square theta A. That is eta C. So eta C coupling efficiency is sin square theta A is nothing but it is numerical aperture. And this numerical aperture is under root n1 square minus n2 square. So this geometrical construction is also very important in order to understand the coupling efficiency. And this NC is equal to NA whole square, NA whole square, when RS is less than RA. For RS is greater than RA, that is the radius of source, is greater than radius of fiber, then the coupling efficiency eta C is A by RS whole square into Na square whole square. Hence, in this way, coupling efficiency expressed, expression provides the estimation for percentage of optical power coupled into the step index fiber SIF relative to amount of power emitted from source. So there are two cases basically. That was when this is optical fiber and this is a source. This is source and this is fiber. So RS is less than RA, first case. The second case was, this was a source and here it is the fiber. RS and this is RA, or something like A. You directly call it is A. So this is A and this is RS is greater than A. So in both the cases, here the efficiency is coupling efficiency Na whole square, and here the coupling efficiency is A by RS whole square into Na square. So what is given? This, suppose this one is 1 n dash, here it is n, n double dash. So this implies that n dash c is greater than n dash double c, because A, this implies A by RS is less than 1, is less than 1. So when the extended source or bigger source is there, here it is smaller, what can say, smaller source, greater the efficiency. Bigger source, lesser efficiency. Something like this. So this one is the basic concept of coupling efficiency. Now, as we said, it depends upon the coupler techniques. Techniques of coupling. First is T. This is also called directional coupler. This is also called directional coupler. So T couple. This is T coupler or 4-point coupler. 4-port coupler. Second is star coupler. Third one is wave front. And fourth is radiation bend fiber. So let us consider the first, that is T coupler. T coupler. T coupler is basically, this is the port that is faded. This is P1, that is P input. Power fed port 1. This is port 2. This is port 2. Here it is port 3. This is port 3. So this power is P2 and this power is P3, P1 input. So how to organize the directivity of a T coupler is defined as the power ratio between one port to another port. One port to another port, which is 0 for the ideal directivity. It is expected that no power is to be transferred between any two ports on the same side of this coupler. Similarly, we can have in case of the 4-port. In case of 4-port, that is, we take this one is, a 2 input and 2 output, 2 input, 2 output. This is input. Here it is P1 power at input. This is power output 2, it is 3, and here it is 4 port. So what can be possibility? this power is transferred from here. This power is transferred to this point. From port, this power is transferred to this, and this power is transferred to this. And we can again have the same power is transferred here and here in this way. So P1 the power fed at port 1 is P1, which is equal to P2 plus P3. This is P2 power, here it is P3 power. P4 is called isolated port, as no power will reach at this port ideally. Power emerging from port 2, power emerging from ports, that is port 2 power is greater than equal to power from port 3. So let us define the same parameter of the couplers. First is tape loss. First parameter is tape loss. It is represented as PL tape. So PL tape is nothing but minus 10 log base 10 P3 upon P1. P3 upon P1. Or P3 upon P1 is equal to 10 to the power minus PL tape by 10. This is somehow we can have transmission loss between the input and tape 2. And second one is throughput loss. PLTH. P. Throughput loss. It is symbolic and defined as, and this is defined as minus 10 log base 10 P2 by P1. P2 by P1. So transmission loss between the input and favored port 2. Favored port 2. Third one is directionality loss is PLD, and this is defined as minus 10 log 10 P4 by P1. P4 by P1. Loss between input port and port we wish to isolate, P4. And the fourth one is excess loss. It is PLE, excess, and defined as minus 10 log base 10 P2 plus P3 upon P1. P2 from examples of this excess loss is radiation, loss due to radiation, scattering, loss due to scattering, absorption, loss due to absorption, and coupling to isolated port. So all these losses are encountered in the excess loss. Now, relationship between PL throughput and PL tip. These are two prominent power. Now for ideal coupler, we have P4 is equal to 0. So P1 is equal to P2 plus P3, or P2 is equal to P1 minus P3. It is equal to P1 minus P3. So we have PL through is equal to minus 10 log base 10 P2 by P1. That is minus log 10. P2 is P1 minus P3 upon P1. So this is minus 10 log base 10, 1 minus P3 by P1. And this is minus 10 log base 10, 1 by 10 to the power minus PL tape divided by 10. Divided by 10, P3 by P1. Because P3 by P1 is L10 that we have already discussed. So PL throughput divided by 10 with minus sign is equal to log base 10 P3 upon P1. Log base 10 P3 upon P1. So this one is the relationship. In order to make the concept, we take the example calculate the various parameters of the given coupler. Splitting ratio is 4:1 first. Second point, P1 is equal to P2 plus P3, that is 4 plus 1 is 5. At port 2, the ratio is 4/5, and at port 3, the ratio is 1/5. And while port 4, this is 0. So this is 80%, and here it is 20%. 80%, 20%. Solution first is throughput loss is -10 log base 10 P2 upon P1. That is -10 log this 4/5. So this is 0.97 dB. 97 dB. Second is tape loss. Tape loss is -10 log P3/P1 -10 log 1/5. That is 0.699 dB. Third one is excess loss. Excess loss is -10 log P2 plus P3 upon 1. That is -10 log 1/5 plus 4/5. That is 5/5. So it is 0. And directionality is -10 log P4/P1. That is -10 log this 0/1. So this is infinity. So what we find? We find is first PLTSP is plus 0.97 dB. Then PLTAP is plus 0.69 dB. And PLEXS is 0. And PLD directionality is infinity. So in this way, we can have the various concept of the coupling and the efficiency of the coupling.